All right, so the next slide is showing you, instead of doing on the board, just for the sake of brevity, how we would find the capacitance of a cylindrical capacitor. So you could create a cylindrical capacitor where you'd have an inner core that was a cylinder and then an outer core that was a hollow cylinder. That would create an electric field between them if they had opposite charges on them. And so in order to solve this, I used a Gaussian surface. I put this Gaussian surface between the two plates. We've done that Gaussian surface before, so the end caps, there's no electric field that goes between them, so that term goes to 0. Solving for the flux, we just have E times A. That's our favorite simplification. Plugging that into Gauss's law, we have Q is equal to E naught times the flux. And then the area of a cylinder is what goes in here, 2 pi r times L. We rearrange that and solve for the electric field. So we've done that before. We solved for the electric field for a cylinder, around a cylinder. We can put that into our equation for potential, and you'll notice that the integral is going from negative to positive. That's why there's no minus sign on that integral. Everything gets pulled out except for the radius. Obviously, the length of the capacitor stays constant, the charges stay constant. So we just have our friend dr over r that we integrated earlier. That was the natural log. So we get this natural log equation. So if you needed to know the voltage on a cylindrical capacitor, you could use that equation without having to rederive it. And then capacitance is just Q over V. And so you get the this big nasty with the natural log in the denominator. Spherical capacitor, I didn't go through all the nitty-gritty details. It's very similar. And here's the capacitance for a spherical capacitor. So you can grab the things in boxes. You don't have to rederive. You don't have to rederive this equation for voltage since we've shown it in class. You can use these if you came to a problem that had them. So these two examples, I think, are doing the integration, so I'm not going to show that in class. And these don't really come up that often, so just refer to this slide if you come to a problem that requires cylindrical or spherical capacitors.
Would a spherical capacitor ever exist?
No, it's completely theoretical. I mean, I guess, but it wouldn't be a perfect sphere on the outside because you'd have to have like a rod going into the middle one, and then the outer shell with a hole in it for that rod. It doesn't sound very practical. So there might be an application, I just don't know of it. I don't even know, I can't even think what you would use that for.
Or how to implement it practically.
It just doesn't seem efficient, yeah. I mean, we can solve, this is like our favorite thing in physics, is to create these nonsensical problems. That's right, that's right.
The horse has to be a perfect sphere.
That's right, spherical cow in a vacuum.
Unless you were like, the inner sphere is like the world or something, and you created this outer sphere so that charges would acquire from whatever happened in the solar system acquire on the outside, and then
like our whole planet would be basically a battery.
You'd have maybe a point where it collects or something, you know. And then
That's a cool idea. I mean, but you need a clear conductor so that we actually got sunlight through it. But they have these exotic materials that are clear conductors. Yeah, that's kind of a cool idea. Maybe when we destroy everything else on this planet, we'll just put a big shell around us and make the planet one big battery, and then we'll just live on the moon. All right, so I showed you our most basic circuit already. That was the battery and one capacitor. That is not a very practical circuit. And so we know that circuits have more than just one capacitor in them. So we're going to take it one step at a time. today we're doing just capacitors. Next week we'll do just resistors, and then we'll talk about what happens when we put those things together. And we, in this class, don't get to like super complicated circuits. You guys will take circuits for that. So we're just kind of doing the baby steps today, and we'll find out what happens if you've got multiple capacitors in a circuit and what to do about it. So what we like to do is reduce that down to what would it be if you've got multiple capacitors in a circuit. I'll just draw like a crazy circuit, for example. Okay, like a whole lot of capacitors, right? And one battery over here. What we can do is we can reduce all these capacitors down to a single capacitor that has the equivalent capacitance of all of those. And so that's what we're doing for the next couple slides. So equivalent capacitance is the value of a capacitor that could replace a combination of other capacitors. If you've got capacitors that are in series, so what does that mean? In series, sounds like they're in a line, yeah. So this is what capacitors in series look like. And then just so you're aware, if there's a bend in the wire like this, they're still in series. So I could draw all these capacitors as long as the wire doesn't split, there's no junction, then all these are in series with each other. So we can replace all of these capacitors in series with one capacitor, and how we would calculate the capacitance of that is we have this complicated formula here for capacitors in series. So the equivalent capacitance would be, 1 over the equivalent capacitance is 1 over the capacitance of all the capacitors in series. So we've got 1, 2, 3, 4, 5, 6 capacitors in series, so we would have 6 reciprocal terms for those capacitors. And then the part that everybody tends to forget is once you get your answer, you've got to flip it in order to get your equivalent capacitance out of it. Okay. So analyzing the capacitors in series in a little bit more detail. Okay, so if we look at these plates, so the battery, if this is connected to a battery over here, we said that the battery is going to attract negative charges to the positive side of the battery, leaving this plate positively charged. And so if there's 4 positive charges on this plate, that's going to attract 4 negative charges on the other plate. So those negative charges come from somewhere. They're going to come from this capacitor down here. So 4 negative charges go up here. And that's going to leave this plate with 4 holes. Yeah, maybe I'll move that off there. And then if there's 4 holes on this plate, then 4 negatives are going to make their way over here. So we see whatever charge this plate has is going to be the same as the charge on that plate. Q1 equals Q2 for capacitors in series. And then going back to our definition of Q, I think I just erased it. Q is equal to C delta V. So capacitance 1 times delta V equals capacitance 2 times delta V. Let's see, where was it going with that? So this from here, well, the battery creates its potential difference from here to here, delta V of the battery. And if there's nothing else happening, there's no other devices along this wire, you can extend that delta V to be from this whole top to this whole bottom. So from here all the way to here is V battery. And it just so happens, we're going to talk more about this next week, that whatever potential the battery creates, potential difference the battery creates, that's going to be the potential difference that's used up by the devices in here. So there's a potential across this capacitor and a potential across this capacitor, and they've got to add up to equal the potential of the battery. So delta V1 plus delta V2 has to equal delta V of the battery. So if we replaced this whole thing with an equivalent capacitor and the battery, and then this is our equivalent capacitor, then the equivalent capacitor would have delta V of the capacitor EQ would have to be the same as the potential difference across the battery. So rearranging this business, this is kind of convoluted now, but if we rearrange all this, delta V is the same thing as Q over C1. Delta V2 is the same as Q over C2. And that would equal the equivalent capacitance. The equivalent capacitance is Q over CEQ equals delta V bat. So we can plug that in down here, Q over CEQ. And so that's where this equation came from. If you just cross out the Q's, you'll see that the equivalent capacitance equation is what you're left with. Okay, any questions about capacitors in series? Okay, so the next thing we're going to look at is how we would reduce capacitors when they're in parallel. Man, everything got all wonky in this presentation. So over here really quick, I'll draw you capacitors in parallel. All right, so this is what we would see if we had a bunch of capacitors in parallel, like that. And so this one's easy. If this is C1, C2, and C3, you could replace those with an equivalent capacitor that just adds up those three capacitances. And then over here, I'll do the nitty-gritty breakdown. Okay, so you can see this part of the board?
Yep.
Okay. Okay, so again, starting out by talking about what the charges are going to do from the battery over here. The positive charges on the battery are going to attract negative charges from all of these plates, since this wire is just going to pull them all over. So a bunch of negatives leave these plates and move towards the battery. And so you get the same number of negatives on each of these plates. No, that's not true. You might have different numbers here. So that the number of charges is going to be dependent on the capacitance of each of these capacitors. So this guy is also going to have an equal number on the top and bottom plate. But what is the same is this potential difference. So the battery potential difference, you can say, is valid from this wire, the top of this wire, all the way to this bottom wire. This bottom wire, we say that's the negative side of the battery. But in terms of circuits, when we say negative side, we mean 0 volts. So everything is from 0 volts upward, even though we say negative. So everything along this line, if you had a voltmeter, would measure 0 volts. So everything, if you moved up this wire, it would all be 0 volts, because as long as there's no device interfering, then this is basically all connected to ground. 0 volts is what we call ground. And that means that this wire, they're all connected to the positive side of the battery. There's no devices interfering, so everything along this wire would measure the high voltage of the battery. So if that's your 1.5 volt AA battery, then you'd measure 1.5 volts anywhere along these wires. So that means that the potential difference across every capacitor is equal to the potential difference across the battery. So let me see. I'll call those 1, 2, and 3, and then just summarize it down here. Okay, and then, okay, that's how we do it. So the thing that is changing, we see, is the charge on each of these plates. So if we have our equivalent capacitor that could be replacing all 3 of these capacitors, it's got the same delta V. So delta V battery equals delta V of the equivalent capacitor. And the charges that build up on this plate would have to be equal to the sum of the charges on all of those plates. So Q equivalent is equal to Q1 plus Q2 plus Q3. And then putting in our definition, we'll make these lower cases. Our definition of Q was C delta V. Actually, I don't need the subscripts because we just established that all those delta V's are the same. So if you cancel the delta V's from the equation, then you can see how we get CEQ is C1 plus C2 plus C3. So the end goal then is we've got to combine these two principles into how we could reduce this big circuit, which has both capacitors in series and in parallel. And the key point is you cannot do it in one single step. Don't even try it, unless you've got your black belt in circuits, which I don't. So what we do is we look for combinations of capacitors that are in series or are in parallel, and we'll reduce those combinations one step at a time until we slowly get down to just one final equivalent capacitor in the circuit. All right, so this is really hard to do. Well, maybe not, but we do have a simpler one we can try in the examples. And if you guys are feeling good, then we'll try this one. Okay, so example 24.6. The circuit we're given, actually I don't know if that red shows up very well. So this has 1, 2, 3, 4, 5 capacitors. $24.6. And they don't all have the same capacitance. 3, 11, 12, 6, and 9. All right, so I've given you some things to think about. So my first question that I have on this example for you is, how do we know a capacitor is in series with another one?
They should be on the same line.
They're on the same line, yeah. And there can't be any wires coming out between them. So you can't have like
You can't have like a junction.
a junction, right? Yeah, that's the word for it. So these two wires are in series, but if there was a junction with another wire splitting off between them, then they would no longer be in series. So that's how we figure out whether something's in series. Now, how do we know capacitors are parallel with one another?
The same side of both potentials, basically.
Okay, so the same side, top and bottom, are going to touch the top and bottom of both of them. Like that. And you couldn't add extra capacitors in here or extra wires in here, then things wouldn't be in parallel anymore. Okay, so we want to look for the smallest grouping that we can that's either in series or in parallel. So what's the smallest grouping for this circuit?
12 and 6.
The 12 and 6, and they are in series. Okay, so for this group, what I'll call that CEQ1. How do we find the equivalent capacitance?
There's just
1 over 12 plus 1 over 6. Inversed. All inversed.
Okay, so we could do that in our calculators. If we're having to do this by hand, you can do the common denominator thing and do times 2 times 2. So you'd have 1 over 12 plus 2 over 12, and that would give you
4.
3 over 12, and then inverse that, and then you get 4. And what are the units?
Microfarads.
All right, microfarads.
also you could just do Q1 times Q2 divided by Q1 plus Q2, so it'd be 72 divided by 8.
Yep.
Q?
Or I meant C.
Ah, yeah.
I didn't, sorry.
Yes, you can. So then what I like to do is then redraw this circuit simplified. So now I have the 3 still, the 11 still, and then this equivalent capacitor CEQ1 on this right-hand side, which has 4 microfarads. And then this guy at the bottom, which is 9 microfarads.
So now you see that 3, 11, and 4 are in parallel.
Okay, so does everybody see that? Anybody who hasn't taken circuits not understand how we did that? There it goes. So everybody is comfortable with that? We see that these 3 capacitors are in parallel? Okay. And so our parallel rule, what do we do to get the equivalent capacitance of these 3? Add them all up. Okay, so 3 plus 11 plus 4 is what? 18. Okay, I know I'm running out of room up here. I don't want to erase the other board just yet because we're using it. So now we have, I'll call this CEQ2, which we said is 18 microfarads. And we still have our 9 microfarad guy left. So these 2, series or parallel? Series, yeah. So how are we going to find the final equivalent capacitance? There we go. And so what does that give us?
6 microfarads.
So this would be the fraction, and then you inverse that, and you'd get 6 microfarads. And so if you're OCD and you want to draw your one final circuit with 1 capacitor in it, you could do that, and you'd say, I'm done. I have 1 capacitor. That 6 microfarad capacitor is equal to all 5 of these capacitors we had before.
You laugh, but my circuit's 1 professor.
Yeah, you did that?
Yeah. You're wrong if you didn't have that final.
Oh, really?
Yeah, the whole homework is wrong.
If you didn't draw the little picture?
Last one.
Okay. All right.
I found that out the hard way.
Did you?
Harsh.
That is harsh. I don't care if you don't even draw the pictures. That's entirely up to you whether you want to draw the equivalent circuit as you go. But I do want to see your work here, so I need to see what you calculated. If you just give me your final answer, you'll lose points. So I need to see what you calculated the whole way through.
Now, for those of us who's already taken circuits, there's a symbol for parallel. Are we allowed to use that?
Symbols for parallel, yeah.
Okay,
Yeah.
double dash.
Yeah. As long as I understand your methods and just keep asking me every time, then that's fine. So like when we get to multi-loop resistor circuits, I'll teach you guys mesh analysis, like base mesh analysis, but not super mesh or whatever. I'm not going to teach you guys nodal analysis, but you can use nodal analysis. I can understand nodal analysis, but if you use something that's not mesh and not nodal and not the basic algebra method, then I really won't know what you're doing. Yeah.
Please go over the top and use phosphorus ones to figure out.
And then I will make you come and teach me. That's what I'll do. If you use something I don't understand, then I'll make you sit down and explain it to me. Okay, so everybody have this down. Is it okay? Dave's still writing. That's fine. Is it okay if I erase? Yeah. Okay. I just want to give us a little bit of room. So this really big circuit. All right. So everybody who's had circuits has to zip it. Okay. So those of you who haven't had circuits, help me reduce this circuit. And there's a couple places that we could start. So what are the smallest groups that we can reduce? These two, so we can reduce these. And we could, so let's say these all have the same capacitance. They're all capacitance of C. So we can reduce these two, and so that, I'll call that C1. And how would we do that? Capacitors in series.
1 over C. What is it? C1, C2?
Yeah, that's what I was gonna say. If you actually assign them numbers, it'd make it easier for them.
Fair enough. So they all have the same value. C4, C5, C6, C7, C8, C9, and C10. So I'll call this guy C23. And so just to remember that these have the same C value, I'll drop the subscripts in our calculation. So, so what does this come out to?
What's C over 2?
So this would be 2 over C, and then we inverse it and we get C over 2. Okay. All right. And so that part we can erase and replace with C23 equals C over 2. And can I use that result anywhere else?
C4.
C4 and C5? Anywhere else? Yeah, does everybody see that 9 and 10 are in series? Okay, good. Okay, now what's the next smallest grouping?
7 and 10, 9, 10.
7 and 9, 10. So these guys are in parallel. All right, so how are we going to find C7, 9, 10?
So C plus C.
All right, yep. Everybody else see that? Okay. So what does that give us? 3C over 2? Okay. C7, 9, 10 equals C, 3C over 2. Okay, and what's the next smallest grouping?
So 2 in the middle.
The 2 in the middle?
And then 7, 9, 10 are the same, right? Are they?
7, 9, 10 are not, they're not in parallel with these two because these guys are in the way.
So just 23, 4, 2, 3, 4, 5.
I'm going to wait on these guys. Okay, so I want to actually wait on these guys. The smallest grouping that I want to deal with first is, yeah, these three, because once I get these down to 1, then all 3 of those are in parallel. Yeah. So that would be C6, 7, 9, 10, 8. And the series equation, so we've got 1 over C plus 3C over 2 plus 1 over C, all to the negative 1. Oh, not 3C over 2, it would be 2 over 3C. So we have to do common denominator here, right? 3 over 3, 3 over 3. So 3, 4, 5, 6, 7, 8. So 8 over 3C to the negative 1, 3C over 8, yeah. Okay, and then we already kind of said the next smallest grouping would be these three in parallel. Okay, so that's C, 2, 3, 4, 5, 6, 7, 9, 10, 8. So we got C over 2 plus C over 2 plus 3C over 8. And let's see, 4 over 4, 4 over 4. Was it 11 over 8? Okay. All those digits. All right. So the last two capacitors, are they in series or parallel? Series. Okay, so that's our final CEQ. And series, so it's 1 over C plus 8 over 11C. And to the negative 1.
So 11C over 20.
Okay. 11C over 21. And there, if we wanted to appease Saban's circuits teacher. There we go. So it's not hard, it just takes a while. Yeah, and takes a lot of practice. And so the book doesn't have a whole lot of like really big ones to practice with, but you can just make up anything, right? And just practice and compare with your friends, you know, be a fun Friday night activity. Your ex-friends.
That's actually how I learned.
Really, you just have your friends write up the craziest circuits and then you try and solve them?
Well, I had a guy that was helping me. He was kind of tutoring me. So what he would do is I have a whiteboard at home also. He'd just draw up some crazy looking circuits and have me reduce it down as much as I possibly could.
Yeah.
Yeah. And finally it just clicked.
Yeah, I think that this is one where you can just practice and you can make it up whatever you want. And if there's two of you that know the rules, then you can have it be a little competition, you know? It is a good party game. I'm going to have to remember that.
Forget to put the series to the negative 1, you have to take a drink.
There you go. That's right.
It's kind of like pool. The more drunk you are, the better you're at it.
I guarantee you, if you play this game, you're going to like physics more. All right. So any questions then about reducing circuits? All right. I think you guys did awesome with that. So we are at a nice place to take a break. And we'll do that and then finish.